So number 8, we have a bicycle that's turned upside down while its owner repairs a flat tire. A friend spins the other wheel and observes that drops of water fly off tangentially. She measures the height, over here, that each drop reaches. A drop that breaks loose in the tire on one turn rises 54 centimeters above the tangent point. A drop that breaks loose on the next turn rises 51 centimeters above the tangent point. And the radius of the wheel is 0.381 meters. First question, why does the first drop rise higher than the second drop? Well, if you think about it, the drops are being launched off the wheel with some initial velocity. What must be true? The first drop went higher than the second drop, so it must have started out with a greater initial velocity. Guess I should call that V0. And so basically the wheel must have been spinning faster when the first drop was launched, thus giving a greater launch velocity. Now part B, neglecting air friction and using only the observed heights in the radius of the wheel, find the wheel's angular acceleration. Now, this is interesting. We don't have the time, but we do know that the wheel is going to go around exactly once between those two drops. Basically, we know theta, which is going to be 2 pi radians. Oh, there we go. Well, how would we solve for angular acceleration or regular acceleration if we didn't have time? Well, you might remember this equation. It's the one that we have that doesn't have time in it. And the rotational equivalent would be this. But you might say, oh, wait a second. We know theta, but we don't know omega final and omega initial. Well, we can actually calculate that. If you remember the direct conversions between angular motion and linear motion, omega can be calculated by taking the velocity divided by the radius. That's just rearranging our equation. You still say, oh, great, but that means we need to actually calculate the initial launch velocity. How are we going to do that? Well, probably the easiest way is just with energy. In this case, the drop, when it leaves the wheel, starts out with kinetic energy. And I'm going to set h equals 0 to the point where it's released. And then at the end, it's going to stop briefly up here at top. And at that point, it's just going to have gravitational potential energy, mgh. The work done in this case is 0. So for the first drop, we get 1/2 mv squared plus 0 equals the final. And please notice here, the mass of the drop cancels out. I don't even have to pick a mass for it, although you could. And if you solve it then, we'll discover the first drop flies off with a velocity of 3.25 meters per second to reach that first height that we talked about, 54 centimeters. Dividing it by the radius of the wheel, we get omega. And so this would be the initial omega of the wheel. It was going that fast to launch that drop that high. And now we can do the same thing with the second drop. The second drop rises 51 centimeters, or 0.51 meters over here. And doing the same process, we can calculate its velocity. Notice it's a little bit less than before. It doesn't go as high. And we can figure out omega. And in this case, this is omega final. This is the final velocity of the wheel after it rotated through 2 pi radians. Plugging in the numbers now, we can solve everything. So our delta theta is 2 pi. We can solve now for alpha, the angular acceleration. And if we do that, we'll discover that the angular acceleration is this. Notice it's negative, meaning the wheel is losing angular velocity. This one is fairly complex. It requires lots of equations. Is this the only way to solve for omega? No, there's some other ways, but I thought this might be the clearest. Good luck. This one was tough.